Okay, so here's where we left off. We had this function, f, was the blue one. G was the red one. Okay, and then we found this angle of intersection, and what was that angle? Was that 3/4? Inverse cosine of, was it 3/4? Or was this one 3/4? This one was 3/4. So we'll call that theta 1. And then this other key angle was, what was the meaning of this angle here? Theta 2 was cosine inverse of 2/5. And what was that one about? What was of interest in that one? Hold on a sec. Turn this off. There we go. What was of interest in that second angle, theta 2? No, I think those were right. Yeah, those are right. So the first one is cosine inverse of 3/4, and then cosine inverse of 2/5. Because 2/5 is less, right? It's less than 3/4, and the x-coordinate would be less. So that's right. And what was the significance of this angle? So this angle was the angle that gives the same radius, or the same r value for the two functions, therefore the intersection point. Okay. This one, what was the case with that second one? Yeah. Okay. So meaning what? That r is. Yeah, so that was the angle for which r is 0 on this f function, right? So it comes in, and there's some angle before pi over 2, right? Because we're still less than pi over 2 here with these negative r, right? These values are negative r for angles just less than pi over 2 up here. So this was that angle such that r was 0, f changed from positive to negative values of r. Okay, so we want to recall how area works. So just let me put a little sketch up here. So the way area works is we have some r as a function of theta, and I'll call it h. I'm only using f and g. And it's to quantify these regions. The regions are such that are like this. They start at some first angle, theta, so theta A, I'll do theta A and theta B. And we think about, that's the independent variable, theta, right? And it's going to sweep from theta A to theta B. And as we do that, we're going to sum up what kind of elements? Remember what they were? Yeah, like triangular slivers. Starting at theta A to theta B. So you got to think about these, like if r is positive, these are sweeping, right? Sweeping counterclockwise, and we're going to accumulate these little triangular slivers counterclockwise from a starting angle to a final angle. So having that mindset is really important for figuring out how we're going to set up expressions to represent these areas. Okay, you've got to really think about that. Our regions always will come to a point at the pole, and then we're going to sweep counterclockwise from a starting angle to a finishing angle, accumulating these triangular slivers. Accumulating triangular slivers, and we saw that area from theta A to theta B was the integral from theta A to theta B, 1/2. So in this case, h of theta. And we derived that last time, remember? So that's going to give us a sector type area, right? That comes to a point. Comes to a point at the pole. Something of a piece of pie with a weird shaped edge, right? Whatever the function however the function shapes the edge. Okay, so we got to use that mindset, and I'm just going to give all kinds of different regions here, and we're going to set up different. So let's try. What should we try first? Let's try this. Can you set up? No. Let's do the real easy one first. Let's do this first. Okay. Can you set up an expression that will find that area? Can you set up an expression that will find that area right there? What would, again, thinking about, we have some starting angle and some finishing angle, right? Swept counterclockwise, and accumulating triangular slivers from the pole out to the function. So what expression will calculate? So this is, hopefully this is easy. Katya, do you think you know what this is? The expression, right? So the expression that'll give that red area. 0 to pi over 2. 1/2. What do you think? Agree? Nice, easy one to start with, right? Nice, easy one. Starting angle 0, finishing angle is pi over 2, and we just have that curve, cosine theta plus 1, is our outer boundary, right? It's our outer boundary, so that's perfect. Next one. Here we go. Can you do this? How about this one? Set up an expression to find the area of that region. Where's Timothy Becker? How'd it go? Do you think you got it? Okay. Okay. What do you think? Did you get it? Yeah, that's it. That's it. So the first angle here is angle 0, and we think about what triangular slivers for increasing theta, and then the last angle is going to, so it's a little bit tricky to see here, but you still got to see it as what, coming out to there, coming out to there. Think of these triangular slivers coming out to there, and where's the last one? At angle theta 2, cosine inverse of 2/5. So that's right. And so whether you write the actual rule or use function notation, it's the same, right? So here we could have put g of theta, right? We could have put g of theta there. Here we could have written 5 cosine theta minus 2. Questions on that one? Okay, now I want the purple shark fin. How am I going to write an expression to give me the area of the purple thing here on the right? Which I'm calling the shark fin. Did I change anything? I took away some distraction maybe, but it's the same thing. Okay, volunteer who thinks they got it. Griffin wants to do it. Tell me. Okay. This is what he's offered up, theta 1. So theta 1 being cosine inverse of 3/4. Yep. And then if you had, again, you could put 5 cosine theta minus 2, because that's equal to that. Also, cosine theta plus 1. What do you think about what he did? Right, yeah, so this is kind of like our situation where we had the area between curves, right? Area between curves. And you're going to take what? Take that whole shaded region, which would be this one, and subtract off the olive green region, which would be this one. And you'll be left with the purple shark fin. This thing here. Does it make sense? Any questions with that? Okay, next one. How many, just for my own, how many people came up with that before we started? Okay, so about half, right. Good. Next one. Okay, so it's too dark. Not enough contrast. No. What's that?
I think the teal color isn't strong enough to offset it.
Yeah, I know. Okay, the black region. I want an expression to calculate the area of the black region. A visual hint, and you can see if either you're doing it right or it helps. Let's see, so. Here's a visual hint. Ready? Watch. Does it confirm your answer, or do you change your answer? I'll show it again. Show it again. This is how to think about it. This is how you got to think about this. Ready? Watch. Okay. 1 or 2 more minutes. So now that's what everything that's shaded was what was black before. All right, where's Dylan? Is Dylan here? How'd it go? What'd you think? Okay. Theta 1 to theta 2. Okay. Did you say plus? He wants plus. Okay. Okay. I want to put that one first if that's okay. All right. All right, he wants the integral from 0 to theta 1 of 1/2 g theta squared plus the integral from theta 1 to theta 2 of f squared, 1/2 f squared. What do you think? That's it. Yeah, got it. Nailed it. So, and that was exactly what I showed you, right? So that red region is just integrating f or 1/2 f squared from 0 to theta 1. And now we're going to add on the second piece, which is, oh, sorry, g. The red piece is integrating g. And then the blue piece from theta 1 to theta 2, 1/2 f squared. Okay. Questions on any of these examples? Okay, so let's look at something different. How about, let's sketch, for practice here, let's sketch r equals 2 sine theta plus 1. No calculators. Sketch 2 r sine theta plus 1, and we'll talk about some areas with that one. So that's a nice, easy one. Hopefully by now, most of us can get that. As theta goes from 0 to pi over 2, what does r do? 1 to 3. Increases from 1 to 3. Like that? Okay? And then we'll do one more for you. So then as theta goes from pi over 2 to pi, what happens to r? Right, back to down. It decreases to positive 1. So that's 0 to pi. Okay, very good. Let's move on here. Where is Christina Tope? Christina here? Did you get what happens after that? So next, so from pi to 3 pi over 2. To negative 2. So it's gonna, she's saying in this next quadrant, it's gonna decrease to 0, hit 0 somewhere, and then go to negative 1 or negative 2? Okay. So can you, on the fly here, can you get it, can you say what? I think you had it right. It's just not, I don't think it goes to negative 2. Just negative 1, right? So somewhere in here, it's going to keep decreasing, and somewhere in this quadrant, it's going to pass to the pole, because r will be 0. And then by the time it gets to 3 pi over 2, it'll be at negative 1, which is up, right? Negative, so at 3 pi over 2, positive r is down, negative r is straight up. Okay? Last quadrant. Jacob, you're up.
So then it's going to decrease to 0 as it gets less negative. So it'll increase to 0.
Okay.
As it curves around, and then it'll go back up to 1 by the time it gets to 2.
Okay. Yeah, so as the angle goes from 3 pi over 2 to 2 pi, the r is going to increase, and at some point increase to 0, and then keep increasing to 1. So it's going to finish off. Okay. So what do I want to find the area of? Of course. What do I want to find the area of? The loop, the inner loop. What's the area of the region inside the inner loop? 2. You're finding area 2. Anybody think they have it? Yeah. Tell me. Okay. Okay. And do we know that one? Do we know that angle? Where sine is negative a half? Which one? Seven pi over 6, and you want to go to 3 pi. Okay, cool. All right, so you want to use 3 pi over 2. That's fine. Okay. So then to get the area, it would be what? Uh-huh. Okay. This is what she's offered up. 2 times the integral from 7 pi over 6 to 3 pi over 2, 1/2 the function squared d theta. Will we get it? And then you could have also done integral from 7 pi over 6 to 11 pi over 6, not multiplied by 2. So that would just take it all the way around. Okay, and then it goes without saying, we're setting all of these expressions, but if we wanted to find a numerical value for the area, just should mention that you would be evaluating the integral, right? So this would be, we're going to get lots of trig integrals, right? We did that sine squared, which remember how to do sine squared, using the identities, undoing the chain rule, all that stuff is going to go into finding the actual value by hand, okay? Evaluating the integral. Questions on that or comments? Okay, question. In terms of A1, so A1 is then the black shaded region inside the curve and outside of the loop. In terms of A1 and A2, what would this calculate? There's a good question. I'm going to integrate this from 0 to 2 pi. I want you to tell me, in terms of areas A1 and A2, an expression of A1 and A2, what will that integral give you? Go. So add this to help you. So I'm going to actually show the thing sweeping out now, okay? And imagine how area works in polar, okay? So here's 0 to pi over 2. What will that give you? Here's pi over 2 to pi. What region will that give you? So then here's pi to where r is 0. Okay, then here's the loop. And then here's where r equals 0 back to 2 pi. So, suggestions, what do you think? Somebody new. Somebody who's not so, yeah, what do you think? A1 plus A2 has been suggested. What do we think? Yeah. A1 plus 2A2. People are liking that. In terms of A1 and A2, it'll give you A1 plus 2A2. Any other suggestions? Yeah. Or just...
Wouldn't it just be A1 because A2 would be negative?
Okay, just A1. Okay, good. Nice. All right, so we got 3 suggestions. So let's talk it through. Again, I'm gonna increase theta as we do it. Ready? So what will we get for theta from 0 to pi over 2? So here's my question. For 0 to pi over 2, does the integral, does the function know that this loop exists? Has no idea that loop exists, right? So it's still going to take from the pole, it's going to take slivers from the pole out to the thing, right? And then the second quadrant, does it know the loop exists? All right, so you're going to get all of that. If you went 0 to pi, you get all of that area, including the loop. You see that? You get all the black, including the loop, when you went above the x-axis. Okay, then we're going to get this little piece underneath. And then, when we go around the loop, is we going to get positive A2 or the opposite of A2 when we go around that loop? So when you go from 7 pi over 6 to 11 pi over 6 of 1/2 r squared d theta, are you going to get A2 or are you going to get the opposite of A2? Because r's are negative, right? R's are negative in that loop. So is it going to be positive A2 or the opposite of A2? But notice, what are we doing to r? Squaring it, right? The function calls for squaring it. It doesn't know whether it's positive or negative. That integral formula does not know if r is positive or negative. So are we going to get A2 or the opposite of A2? A2. So what, we just added that loop in again. And then the last little bit. So if you said A1 plus 2A2, you had it right. That's right. So the question is, write an expression, an integral expression for A1. How would you write an integral expression for A1? And that includes this little part down here. So A1, oops. Oh, jeez. So A1 includes all this stuff down here too. So you want A1, everything inside the outer curve except the loop. How would you write an integral expression to get that? Yes, sir? Okay. So when you go from 0 to pi over 2, remember we did this? Does it know the loop is there? Do you see that you also just got half of the loop by doing just 0 to pi over 2? You see, it has no idea the loop is there, and it's going to take it from the pole, slivers from the pole, out to the curve. That includes half that loop. And then from pi over 2 to pi, again, slivers from the pole out to the... So in that 0 to pi, you get the loop too. And then you come around and you do it again. When you actually do from 7 pi over 6 to 11 pi over 6. All right, so how am I going to get just A1? I want to get just A1. Will be what? Somebody new. Somebody new. I know Griffin and Jacob know. Quick, so we can get out of here. Yeah.
You take the integral from
0
0 to 2 pi.
to 2 pi.
1/2 of theta squared d theta.
Okay.
Minus 2 times the integral from 7 pi over 6 to 11 pi over 6.
This one, yeah. So you're going to have to subtract out 2 of that, 2 loops, right? You're going to have to subtract out 2 loops. 2 times integral 1/2 f squared. And now this is from, what, 7 pi over 6 to 11 pi over 6. Or 4 of these, right? So 4 of these, 4 half loops, but yeah. And then that gets you A1. The area inside the outer curve, but outside the loop. Okay, if you haven't done the course evaluation yet online, please do that today.